Everybody, and thank you very much for joining us on today's CPD presentation, where we're continuing our journey around the steam and condensate loop, with today's presentation being on the topic of steam quality. My name's Dan Wells. I'm the National Consultant Specialist for Spirax Sarco, and today's presentation has been very kindly arranged and coordinated by Project Solutions. For those of you who don't know, Project Solutions are a family-owned company based in West Yorkshire with offices in Teesside, specialising in all aspects of EPC, project design and management. Brian Lawson, who many of you may already know, is actually the technical director of Project Solutions, but he's also the chair of IMechE for the West Yorkshire area. So I'd like to say a big thank you to Projects and Brian, and also his colleague Nikki Baxter at IMechE in the West Yorkshire region. And I'd also like to thank Natalie and her colleagues that have enabled today's presentation at IMechE Birdcage Walk. So today's presentation, it will be recorded and it will be uploaded to IMechE's YouTube channel, but I would also encourage you to use the chat function on the presentation today. My colleague, Steve Bishop, will be facilitating on the chat function, so please do feel free to send him any questions that you may have as we go through the presentation, and we'll read out any questions that there may be when we get to the end of today's presentation. So as we've mentioned, today's presentation is number 8 in the series of STEAM education that we've gone through over the past few months. And today we're really going to understand a little bit more about STEAM quality and the importance of supplying the correct quality or condition of steam for the process. So we've introduced Spirax Sarco as an organization on a number of occasions in the previous presentations that we've gone through. But the one thing that I would like to call to your attention is that very, very useful calculator and configurator that can be downloaded in the form of an app onto your iPhone, onto your Android phone. And there's 2 different calculators there that will be of particular interest. One will assist you with the mechanical design of any steam distribution network. For example, sizing the steam pipes, the condensate pipes, sizing the condensate load, and therefore sizing the steam traps. But it can also assist you for financial reasons. For example, if we know a few key pieces of information, such as our client's cost of water, cost of fuel, then we're able to determine the cost of a unit of steam. And therefore, if we understand if we've got a steam trap or a control valve that has failed, or if we've got a significant mass of flash steam being vented away to atmosphere, by understanding that mass loss, we can determine the financial impact we can have on optimizing a steam system. It can help us understand the return of investment. So today's presentation, steam quality. We're going to look at a little bit about how steam's generated in the energy centre. We're going to look at the potential contaminants that steam can have. And we're going to really drill down and understand exactly what constitutes a poor quality steam. And then we're going to look at how and why so many different processes are likely to have different steam condition requirements. So in previous weeks, we've discussed plant steam. What you can see on the screen in front of you at the moment is what we refer to as the steam condition triangle. So plant steam, that is really the steam that is generated in a typical plant steam boiler and distributed out around site to the various steam using processes. Now, typically, they're going to be some form of heat exchanger. And you'll remember from previous presentations, whenever we're distributing steam onto a heat exchanger or a closed loop system, the steam doesn't actually come into direct contact with the product or with the environment. But of course, we understand that if that steam is going to be used for direct injection purposes, then that steam can result in a point of contamination. And we need to understand that there are different grades of steam that can apply depending upon the nature of the process, what we're actually using the steam for. So before we move on, I just want to remind ourselves of those basic properties of steam. So previously we've discussed steam's a gas. That gas is compressible. So there's a benefit in generating and distributing a higher pressure of steam because it occupies a very small volume and therefore can be distributed in a smaller infrastructure. We know that we don't pump steam. Steam moves in accordance with the pressure drop around a distribution pipework. And we also know that there's a direct pressure to temperature relationship with steam. In other words, we can control the temperature at the process simply by manipulating the steam pressure. We also know that steam is very, very dense in energy compared to other sources of energy, such as low temperature hot water or thermal oils. And we also know that the cornerstone of steam engineering is in the understanding that water, which is the raw ingredient of a steam system, water has got a specific heat capacity of 4.19. In other words, if we want to increase a kilogram of water by just 1 degree, we need to add 4.19 kilojoules of energy into it. And because steam is generated at higher temperatures and pressures than LTHW, that explains why there's so much useful energy in the steam, why it's so energy dense. We also know that steam, as a gas, it gives up its energy by condensing, by changing state from a gas to a liquid. And that explains why the steam uses all of the heat transfer surface area very, very efficiently. So we get a very rapid and efficient transfer of heat energy into the process. And we know that that speed of heat transfer is about 3 times greater than LTHW. But the important thing to bear in mind is that when steam gives up its heat energy by condensing, by changing state, that it's actually only its latent heat that is used by the process. So just to remind ourselves of the steam tables that we've gone through on a previous occasion now, we know that the steam tables, as demonstrated over towards the left-hand side of the screen, it gives us a lot of very, very powerful information. In the first 2 columns, moving across from the left to the right, it demonstrates that pressure to temperature relationship that we've spoken about. The next column, the enthalpy of water or the enthalpy of evaporation, that really demonstrates how much heat needs to be put into the water to bring it up to boiling point. So in the case of bringing water up to 100 degrees at atmospheric conditions, you can see we need to add 419 kilojoules of heat energy. That brings us boiling water. It doesn't give us gas. So if we need to encourage that water to change state and to move from a liquid to steam as a gas, we need to add a further 2,257 kilojoules of heat energy into it. That means the water's now changed state and fully evaporated. And it means that when we combine the sensible heat with the latent heat, it means that we've got a total heat content of 2,676 kilojoules. And we also know that when steam gives up its heat energy and condenses, we know that it's that latent heat energy. It's the energy that we added to the boiling water. That's the energy that passes across into the process. So ultimately, that means that the energy that is left behind in that liquid condensate must be the same as the energy that we added to the water to bring it to boiling point. So previously, we've mentioned that condensate is a byproduct of heat exchange. There isn't enough heat energy present in the condensate to satisfy the process. We need to get that condensate away. But that condensate is still hot water with a reasonable amount of heat energy contained within it. So if we move across now to the temperature enthalpy curve, that demonstrates the journey that water takes as it changes state to produce steam. At 0 bar gauge, 100 degrees, we know that the water will only start to boil when we've added 419 kilojoules of energy into it. That's when the evaporation process begins. But the evaporation process will only end and give us a mass of dry saturated steam when we've added that enthalpy of evaporation. In the case of zero bar gauge, 2,257 kilojoules of heat energy. So that's going to give us a mass of dry, saturated steam. And that's critically important whenever we're talking about steam quality, steam condition. Why? Well, the wetter the steam, then the more likely that steam is to condense out in the distribution pipework. So of course, that's going to represent an energy loss. We're likely to see energy starvation or steam starvation at the process. But if we get more condensate that exists in the distribution pipework, we're more at risk of erosion, corrosion, and water hammer. We're more at risk of any dry steam that's passing across that trapped puddle of condensate degrading. So there's going to be less energy contained within the steam as well. But it also means that if we are using that steam for direct injection purposes, that steam is more likely to pick up droplets of condensate that's going to be entrained within the steam, together with any iron oxide, rust, or scale that exists as a result of that foam being carried out of the boiler. All of that runs the risk of being injected directly into any process that we may be using direct steam injection for. So keeping the steam as dry as we possibly can is valuable for a number of different reasons. The mechanical and maintenance burden on the infrastructure, the loss of massive steam as a result of that distribution loss, steam with very little energy in it at the process. But when we're talking about understanding the steam condition, it means that we're more likely to have steam with less energy in it, and we're more likely to have steam that is contaminated with an excess of moisture and other particulates. So the steam tables, we also know they demonstrate that pressure to temperature and that pressure to volume relationship. And that helps us to understand how we need to control and distribute the steam. But please remember, the steam tables and the various relationships, pressure, temperature, and pressure volume, they are based on the understanding that that steam is being generated perfectly dry and free of air and other non-condensable gases. So that means that we really need to be on top of the way that we're generating the steam in the energy center, in the boiler house. If we're not generating an excellent condition of steam, then the true nature of the steam is going to pull further and further away from the properties dictated in the steam tables. So it's important to look at how steam is actually being generated in the boiler house itself. And those key components that we've discussed in the boiler house, as you can see on the screen above, well, Spirax Sarco don't manufacture steam boilers, but we do manufacture and specify the components that you can see identified in the blue color. And they're typically associated with ensuring that steam is generated, first of all, safely and in compliance with the various regulations. To ensure that steam's being generated efficiently from an energy perspective, to ensure that the steam can be generated as soon as there's a demand by the process. But as far as this presentation is concerned, is to ensure that the steam is being generated at the best possible condition. And we can actually take it one step further back from the boiler house. We actually need to consider the condition or the quality of the raw water that's being used. We know raw water, well, that's the principal ingredient of a steam system. If we're using raw water that isn't of a good enough condition, we're never going to get a good condition of steam being produced. And we're likely to be spending quite a lot of money in treating the water to bring it up to an adequate standard so it can be used. So apologies, I'm showing a map of England at the moment, and I was struggling to find one of the wider European area with this amount of detail. But I really just wanted to demonstrate that the condition of water that is available, it can change over a very, very short distance. So if we've got a steam using site in one part of the UK, and it had got a sister process 20 miles down the road, well, it could mean that they're getting a completely different condition of steam being produced as a result of the changes to the raw water quality that was available. So, of course, the nature of the chemical composition of the water is really going to dictate how we need to chemically treat the water, and maybe even it's going to change the chemical composition of the water in the hot well, in the feed tank. So previously, we've mentioned that the purpose of the hot well, of the feed tank, is to recover as much of that hot water in the form of condensate return as we possibly can. This is the point where we blend that hot water with any makeup water that may be required. And ideally, we want to be keeping the water in the hot well at a temperature of around about 85 degrees. And there are a number of key benefits in doing that. First of all, if we've got hot water going into the boiler, we get less thermal fatigue, less shock, less wear and tear on the boiler. Hot water going into the boiler, we're going to respond and produce steam more rapidly whenever there's a demand. Hot water going into the boiler, we need to consume less fuel to raise steam again. But as far as steam condition or steam quality is concerned, there's another key benefit. And that's because hot water is capable of holding on to far less oxygen and other non-condensable gases than much colder water. So typically we add a small amount of oxygen scavenging chemicals to the hot well just to polish off that last remaining particle content, oxygen content, to protect the boiler. But of course, if we've got water that's held in the hot well much lower than 85 degrees, 50 or maybe even 60 degrees, then we've got a number of different issues. We've got cold water going into the boiler, thermal shock, a little bit of corrosion of the boiler. It means that there's going to be a delay until such a time that the boiler can respond and start to produce dry saturated steam. So that means in those first few moments, the steam is likely to be wet. Wet steam, as we know, has got less energy contained within it, and it's more likely to result in corrosion, erosion, and water hammer. We also know that if we've got very, very cold feed water, it means that we're likely to need to add in more and more of the oxygen scavenging chemicals. And not only is that going to be at a considerable cost, but it means we're fundamentally changing the water chemistry as it adds in to the boiler. So one of the first things we want to do when we're understanding the condition or the quality of the steam that's available on site is look at the temperature gauge. We can't hold the temperature significantly higher than 85 degrees because if we do so, there's a risk of cavitation and expensive failure of those boiler pumps. So the other thing that we want to give thought to with regards to considering the steam condition are the level controls that furnish the boiler. Now, as we know, level controls, they can be mounted internally or externally, and they're typically going to be of a magnetic float, a conductivity type, or even a capacitance type probe. And the magnetic float and the conductivity level control, that's capable of sending a signal to an on-off pump. And the volumetric difference between the pump switching on and the pump switching off again, that can be considerable. So if we're calling for a mass of a much lower temperature water from the feed tank, if the boiler's operating at 10 bar gauge, for example, the boiling point is 184 degrees. So if we're calling from water from the hot well at a very low temperature, could be 50 or 60 degrees, then you can appreciate that that's going to have a significant quenching effect. The rate of steaming is going to fall off. The boiler is going to use a lot of energy to race to start to produce steam again. So there's an energy inefficiency. And the steam that is going to be produced in those first few moments, it's going to be relatively wet, contributing to that erosion, corrosion, and water hammer that we spoke about. So it's far, far better to move towards a capacitance level control pump for the simple reason that that is capable of sending a signal to a modulating pump. So by constantly drip feeding in a very small mass of high temperature water, we can keep the steam in equilibrium with the process demands. We're producing steam not only responsively and efficiently from an energy perspective, it means we're getting a consistently drier and better condition of steam being produced. We also know that the TDS and the bottom blowdown controls are critically important when it comes to understanding the condition or the quality of the steam being produced. Previously, we've mentioned that the chemicals and minerals that are present in the raw water and the chemicals that we add to the feed tank as well are going to behave in a number of different ways. Some of the chemicals and minerals, they will solidify. They'll fall to the bottom of the boiler as a rich sediment, and they need to be removed periodically by opening up a bottom blowdown valve and flushing that sediment to waste. Now, traditionally, that's been done manually. But if we're just opening and closing a valve and purging a mass of hot water to waste, then quite often we're going to be uncertain with regards to the amount of hot water we're losing. That hot water has got to be replaced with a much colder temperature of water from the hot well. So, of course, the more hot water we're blowing down, the more inefficiently we're working from an energy perspective, and the more likely it is that we're going to be producing steam after a significant delay that is relatively wet. So we can keep that bottom blowdown to an absolute minimum by upgrading the controls, by moving away from a manual valve to a valve with a timer on an actuator, so we can ensure that the blowdown is kept to the prescribed minimum. Now, we also know we blow down from the side of the boiler, and that's to address the total dissolved solids. And that's because some of the chemicals and minerals will be held in suspension. And that's what can contribute to that rich foaming layer that we experience in a boiler when we get a high chemical composition. Any fluctuation in boiler pressure, that can result in that foaming layer expanding and being drawn out into the distribution pipework. So that foam will be very wet and sticky, and that will contribute to the erosion, corrosion, and water hammer, steam with very little energy contained within it. We also know that that foam will dry out as scale, and that scale can not only result in further erosion as it passes around the network, but it can bind itself to sensitive heat transfer surface areas, such as sterilizers or plate heat exchangers. And that can result in an insulating layer or a barrier to heat transfer. But whenever we're using that steam for direct injection purposes, we also know that we're at risk of those dried out boiler chemicals entering into that product or atmosphere that we may consider to be sterile. So, just as we can move away from a manual valve to improve the efficiency of the bottom blowdown, we can move towards a conductivity probe that can sit ahead of a modulating valve in the side of the boiler, and it can modulate a very small mass of a high concentration of TDS to waste. The important thing is we want to keep the TDS blowdown and the bottom blowdown at the prescribed level. If we're blowing down too much hot water, not only do we get an inefficiency, but we get an erratic and irregular steam production, and that steam production will be relatively wet in those first few opening moments. But if we don't blow down enough, then we run the risk that that concentration can reach a high point. And if we get a high concentration of chemicals, that's when we're at risk of that foaming layer expanding and being drawn out into the distribution pipework. Now, we also know that we can improve upon a traditional atmospheric deaerator, hot well, feed tank, whatever you want to call it. Because if we can move towards a system whereby we're keeping the hot water in storage under pressure, by elevating the pressure to 0.2 bar gauge, by elevating it to 105 degrees, for example, well, it means we've got a number of key benefits. For one, hot water going into the boiler, less thermal fatigue. We're producing steam more rapidly whenever there's a demand. We're producing steam with less of an energy demand. And because we're generating steam from pressurized hot water, the pressure has actually purged off a significantly greater amount of the air and the other non-condensable gases. So we've got less corrosion. It means we need to add fewer chemicals to the hot well to polish off that last remaining mass of air. So it means we're not actually changing the water chemistry fundamentally, which means we need to perform less blowdown. And that in turn means we get drier steam being produced on top of the energy cost saving there. It also means that we can contain any flash steam losses that may be experienced at different parts of the network. We can bring that flash steam back to the pressurized deaerator, where that flash steam can be reabsorbed into that hot water to keep the energy level at a nice high point. So it's fundamentally important to ensure that we're generating the steam at the best possible condition. But it's equally important that we observe good working practice to ensure that that good condition of steam doesn't then degrade as it travels from the point of generation to the point of use. And we can be distributing steam in an infrastructure that's hundreds, if not thousands of meters in length. So it's important that we've got a good understanding with regards to what we actually mean by good condition. Well, when we're talking about distributing plant steam for the vast majority of heat exchange applications, we mean we want the steam to be reasonably dry. The drier the steam, the more energy there is contained within it. So we need to drain that condensate away. We want to keep the steam free of rust, scale, other particulates that can have an insulating barrier to heat exchange and cause problems with erosion of sensitive pieces of equipment. We want to vent the air away because it causes corrosion and because it's a barrier to heat exchange. And we want to size the pipes correctly. Now, you may be thinking, well, what's pipe sizing got to do with steam condition? Well, we want to distribute the steam in the correct infrastructure because if we're distributing it a considerable distance, we want to ensure that the correct mass, pressure, and temperature of steam meets the process. If it doesn't, then we're going to have some kind of inefficiency or failure of the process itself. So we need to observe the pressure drop method. But we also want to observe the velocity method as well. So whenever we're distributing steam a relatively short distance, we want to ensure that we're distributing it at the correct speed. Typically, steam should be distributed, as a rule of thumb, somewhere between 25 and 30 meters per second velocity. If it's an excellent condition of steam and we're distributing it at a short distance, we may elevate that to 40 meters per second. But if we suspect that the steam is wet, for example, if we've got relatively unsophisticated controls, if we suspect we've got wet steam with an excess of moisture and particulate present in the steam, we don't want to be distributing it at a fast velocity because that's when we're at risk of the various components eroding. And an eroding control valve, for example, well, for one, it's not going to be operating efficiently from an energy perspective. But if it's operating unreliably, then we could have a mass of steam being distributed onto a process when it simply wasn't required. And that could result in product spoilage. So we want to observe the velocity method to ensure that we've sized the steam pipes correctly, and that should be done in accordance with the condition of the steam that it's exposed to. Again, remembering that steam's a gas and not a liquid, we want to design the infrastructure to allow for the condensate to drain away to a low point quickly and easily and not become trapped in any way. So we want to use eccentric reducers with a level plane on the bottom. We want to trap the condensate or remove the condensate with a steam trapping station at the low point. We want to install Y-type strainers with the basket on its side so that condensate doesn't become trapped. If it were to become trapped, we'd be exposing ourselves to the risk of that erosion, corrosion, water hammer, and steam with very little energy contained within it. So, of course, we want to distribute the steam in an infrastructure that observes a rise and fall, typically of a gradient of around 1 in 100. That allows the condensate to gravitate to the low point where it can be removed across the appropriately designed steam trapping point. Typically located 30 to 50 meters apart. We also want to observe that the takeoff, where we're taking dry saturated steam to the process, is done so from the top of the pipework, not from the bottom of the infrastructure, where we run the risk that we could be flooding the process with that liquid condensate that, as we remember, simply doesn't have enough heat energy contained within it. In order to keep the steam quality as high as possible, we need to vent the air away. Two reasons. Air is perhaps the biggest cause of corrosion in a steam distribution pipework. And if we've got corroding pipework, then of course there's the risk that that iron oxide, that rust, can become entrained within the steam that can further cause erosion of sensitive components, or it can find itself being injected directly into that product or atmosphere whenever we're using steam for direct injection purposes. So the two images in the bottom of the screen, they remind us of the purpose of using thermostatic air vents, not mechanical air vents. We use thermostatic air vents because the more air that we've got present within the steam, then the more of an insulating effect we're going to get at the point of heat transfer. We're going to get a barrier to heat exchange. And that's really got its principle in Dalton's law of partial pressures. In layman's terms, it simply means that we could be distributing a pressure of steam to the process that was acceptable, but it means that any air that was entrained within the steam could really be dragging the temperature down. And it's for that reason that we always encourage you to remember that the steam tables are based on the understanding that we've got a mass of steam that is perfectly dry and totally free of air and other non-condensable gases. But of course, we don't live in an ideal world. We need to allow for that air to be vented away. And we do so using that thermostatic trap, that thermostatic air vent at the process, at the very, very end of the distribution line, and at the occasional high point. And the goal is to distribute the steam so it arrives at the process, at the point of use, at the best possible condition. So whenever we're talking about a steam using process, as we mentioned in previous presentations, we could be talking about a plate heat exchanger, a shell and tube heat exchanger. We could be talking about a coil in an air handling unit. But in each of those applications, that's where steam doesn't actually come into contact with whatever it is that it may be adding that energy to. So what's important at this point is to ensure that the steam is dry, free of air and other non-condensable gases, and supplied at the correct pressure and mass flow rate. But of course, if we're using steam for direct injection purposes, it could be for a humidification system, it could be being injected directly into a sterilizer or an autoclave, or it could even be for going into some means of cooking, heating baked beans or soup up, for example. In each of these cases, it means that unless we're generating an excellent condition of steam, it means that that steam is at risk of contaminating the product or atmosphere. So whenever we're using steam for direct injection purposes, we need to measure it. We need to quantify its condition. And we can do that using a standard known as BS-EN 285. That basically means that we're measuring the steam for known properties. We want the steam to be 95% dry or better. Why? Well, the drier the steam, the less moisture there is in the steam, the less the risk of contamination with that water to the process, and the more energy there is contained within the steam. We want it to be free of air and non-condensable gases, typically 3.5% volume of a 100 milliliter condensed sample of steam. Why? Well, the less air and other non-condensables there is in the steam, the more energy there is, the more closely we're operating to that pressure temperature relationship. And of course, we need the steam to be supplied to the process at the correct pressure temperature and mass flow rate. So certain applications, certain processes, they're going to need to measure the steam condition. And BS-EN 285 allows us to do that. But it's always good working practice to ensure that the steam is kept as dry as we possibly can. And when we're talking about steam condition, we do that for three reasons. We use a steam separator, first of all, to remove the moisture. By removing the moisture, we keep the steam dry with a very high energy content. By removing the moisture, we're protecting any instrumentation that may be downstream or ahead of the point of use from the risk of erosion. Remember, if that instrumentation, if that control valve starts to erode, it is now no longer working efficiently or working accurately. And of course, if we are using steam for direct injection purposes, by removing that moisture from the steam, we're minimizing the risk of that process becoming contaminated. So we also have a little Y-type strainer located here, and that's just to remove any particulate that may be present within the steam that could otherwise contaminate a process or create erosion of that sensitive equipment. So it's always advisable to fit these conditioning ancillaries ahead of pressure reducing valves or control valves or flow meters. And it's at this point, once the steam has been appropriately conditioned, that we reduce the pressure. And just to remind us why we reduce the pressure, well, we distribute steam at a high pressure because it occupies a small volume and therefore it can be distributed in a smaller pipe diameter. We reduce the pressure at the process so we can use that pressure temperature relationship to determine the energy that is distributed onto the process, but also because there's more useful latent heat energy present within a mass of steam at a lower pressure. So we can use a self-acting valve in order to undertake that pressure reduction, or we can use a control valve. And the benefit of using an electrically or pneumatically actuated control valve over and above a self-acting valve, well, it operates more responsively, it operates more accurately, and it can also send a signal back remotely to a BMS or a PLC. But the thing to bear in mind is the control valve, it can often experience a number of issues. Two issues: quite often that control valve is oversized. And if it's oversized, then it's going to spend a lot of time operating very, very close to its seat. So that means that the velocity of the steam moving across the control valve could be far greater than intended. And that can result in a little bit of erosion of those sensitive seats. And especially if we've missed off those conditioning ancillaries. If we've got an oversized control valve where the steam's moving at a very fast velocity with a lot of moisture or particulate in it, that control valve is going to fail very, very quickly. So we need to ensure that we've sized the control valve correctly. As a very, very broad rule of thumb, that control valve is going to be correctly sized when it's approximately 2 pipe size diameters smaller than the upstream steam pipe. So we spoke earlier about the impact of wet steam on a process, and the equation above, it shows us how we can calculate the kilowatt requirement of a process, could be a heat exchanger, for example, if we know the mass flow rate and also the enthalpy of evaporation, the energy that was present in the steam at the known pressure. But what we need to bear in mind is that all of these calculations, the equations, the steam tables, they're all based on the assumption that that steam is perfectly dry and free of air. So it's at this point I just want to come back to the steam tables again. And just reiterating the point that the steam tables are all based on a dryness value of 1 or 100%. Basically, it means that if we got steam that was wet, the equation I'm using here is a dryness value of 0.5 or 50%. That could be down to poor steam control, generation, or distribution practices. But if we got steam that was 50% dry at the process, it would be 50% wet. That means we'd have 50% of the energy present within the steam that the process was expecting. So of course, that means that the process will either be calling for more and more steam in order to satisfy its requirements, or there simply isn't going to be the amount of steam required, and so the process time will extend and extend, or we may simply fail to reach the desired temperature of the process altogether. But if we add that to the fact that we could then have a further mass of air or other non-condensable gases entrained within that steam, you can appreciate that wet steam together with an insulating film of air, it means that it's going to be nigh on impossible for us to hit the required process conditions, which is why dry steam and steam that is free of air and other non-condensable gases remains critically important. So we also know that we may be encountering issues at the process, at the heat exchanger, due to a poor heat transfer. Now, it may actually not be down to any fault of the steam. The steam condition may be perfect. It could be down to the fact that we're simply not removing the condensate. And if that condensate backs up ahead of the steam trap, it could slowly start to flood the steaming space. And as we know from that previous slide, there's significantly less energy present in a mass of condensate. So of course, if the steam cannot enter the heat exchanger, the rate of heat exchange is going to slow down significantly. So typical steam using applications. In the food and beverage industry, we could be looking at a jacketed vessel. We know it's important to keep the steam dry and clean. We know it's important to vent the air away using that thermostatic air vent. We also know it's important to drain the condensate away so we're not flooding the steaming space. It's only by doing so that we can keep the rate of heat transfer at the optimal rate. Similarly, with other pieces of capital equipment such as retorts. Now, the steam may actually never come into contact with the process, but we can only get the process up to the required temperature by keeping the steam dry, by venting the air away, and by removing the condensate. But what about when the steam does actually come into contact with an ingredient? It could be in the food and beverage industry. It could be in the pharmaceutical sector. It could even be using steam in a healthcare application. For example, operating theatre humidification. It means that we need to consider steam as an ingredient. It's being added to the process. And that's why we need to refer back to that steam condition triangle that we've referred to. Now, plant steam is going to be perfectly acceptable for many applications, but if there's a risk that that steam could be a point of contamination, we need to apply a HACCP. We need to move up the steam condition triangle. And it's only by moving above the red line and generating chemical-free steam from what we refer to as a clean steam generator that we can guarantee that we're adhering to those standards dictated by BS EN 285 and we're eliminating the risk of contamination. So how's that done? Well, typically that's done by using what we refer to as a clean steam generator. Basically, it's a 316 stainless steel steam to steam generator. We use that plant steam that may have some contaminant present within it. And by using a chemical-free source of water and generating steam in a 316 stainless steel generator, we can guarantee that we're providing steam that will hit the defined requirements. So I'm just going to play a little animation now that will hopefully give you an insight with regards to how we can use a clean steam generator to meet the requirements of the vast majority of critical applications. So hopefully you can appreciate that it's only by generating chemical-free steam in a dedicated generator that we can ensure that the steam is distributed to those critical processes free of air or the non-condensable gases, more than 95% dry, and to ensure that there are no other particulates as a result of the water chemistry that are carried across to the process. But there's also another terminology that we employ, and that's purity. So when we're talking about the quality of the steam, typically we're talking about the energy transfer attributes. For example, how dry the steam is, the air content, and also the superheat. But whenever we're talking about steam purity, that's typically referring to the steam that may contain particulates within it, any corrosion or any iron oxides or boiler chemicals. So certain industries are going to measure the quality and the purity in different ways. When we're talking about the purity in particular, especially when we're talking about a very, very small minority of applications, it may well be that we're monitoring the purity of the steam by taking a condensed sample and measuring the conductivity. And that's typically going to give us an indication with regards to the particulate content of that steam. That would typically be utilized in the biopharma sector, whereas in other sectors, such as the food and beverage industry, it's acceptable to simply just ensure that we're then generating steam in compliance with EN 285 standards. But in the food and beverage sector, there's a further consideration, and that's a standard that we know as EC 1935-2004. And that basically states that any product that comes into contact with foodstuffs has got to be EC 1935-2004 compliant. And of course, steam will come into contact with foodstuffs if and when it's used for direct injection or indeed sterilization. So that means that the steam generator itself must also be EC 1935 compliant. So we also know that the byproduct of steam, whenever we're using steam for heat exchange purposes, we know that the byproduct is condensate. We know that the condensate is produced both in the distribution pipework and also at the heat exchanger itself. And we know that that condensate needs to be recovered for two reasons. One, it's detrimental to the process if it's left there because it doesn't have enough heat energy in it. But if we can recover that hot condensate and get it back to the boiler house, then we can produce a good quality of steam far, far more efficiently. So that means that in order to allow the condensate to move away from the network, we need to ensure that we've sized and selected the correct type of steam trap, which you remember we went through in some considerable detail a few months ago. We looked at how there's no such thing as a universal steam trap, and we need to ensure that we're getting the condensate away from the process at the correct rate. We also need to allow for sizing the steam trap to allow for that increased mass of condensate that is going to be present when we're warming the system up, what we refer to as the warming up load, which is typically 2 times the mass that we experience for the running load, the normal operating conditions. So that's all well and good when we're considering the removal of the condensate on the plant steam side. But when we want to remove the condensate on the clean steam side, we need to remember, first of all, if we're distributing clean steam downstream of the clean steam generator and ahead of the process, well, we'll be doing so in 316 stainless steel pipework. Why? Because we don't want to reintroduce any risk of corroding carbon steel. And it also means that we want to guarantee that we're removing condensate at all times. We're never holding any condensate back because that can impact upon that critical dryness value. And if a trap were to fail in the closed position, there could be a slight risk of a little bit of microbial growth as well. So we need to select a specific type of trap for use on clean steam systems. And as you can see, it can only be the thermostatic trap that satisfies all of these requirements. And that's really demonstrated in the bottom left-hand corner of the screen here. It's got a little element contained within it, and that element should be maintained periodically. Better still, it should be totally replaced somewhere between every 3 and 4 years, depending on the process, and that should be written into the scheme of inspection just to guarantee that we're not further reintroducing the risk of contaminated condensate. And on the topic of condensate, as we've mentioned, we need to ensure that the condensate is being drained away from the process adequately. And that's where the automated pump trap really has got its place. So we know heat exchangers can work at very, very low pressures. If the pressure of the heat exchanger, the pressure that we're condensing that steam at, if that falls below the back pressure that's placed on the condensate infrastructure, well, there's a risk that the condensate won't be able to move across the steam trap. It'll start to back up and flood the process. And if that happens, that's when we're going to have a process design condition that falls out of spec. Now, our first instinct may be to point the finger of blame at the heat exchanger, at the control valve, maybe even at the steam condition, when in actual fact, it may be simply down to the fact that we're not removing the condensate at the appropriate rate. So when we talk about steam condition, condensate is critically important. We need to ensure that we're moving the condensate away from the process in the appropriately sized and selected condensate pump, for the simple reason that, as we've mentioned previously, condensate is not only hot water, but it's also hot water that has been chemically conditioned. The more of that hot water we can recover back to the boiler house, the less energy we need to raise steam, but the more responsively we're raising steam, the less chemicals we need to add to the feed water, meaning we need to perform far, far less of that blowdown. So of course that means that we get less carryover, less foaming, less scaling, and drier steam being produced. But the thing to bear in mind with a condensate recovery pump, especially an electric condensate recovery pump, it can only move condensate as a single phase liquid when it's cooled to 100 degrees at 0 bar gauge. So that means we're going to see an energy loss at this point here. We're going to see a certain amount of flash steam being vented away to atmosphere. And the problem with an excess of flash steam being vented away to atmosphere is, well, not only is it an energy inefficiency, if we've got an excess of flash steam being lost, we've got to replace that condensate that is now going missing. We've got to consume more water. We've got to chemically condition that water. We've got to bring it up to temperature again. It's contributing to that wet steam that we've spoken about. But unfortunately, that venting away, it does need to take place because we need to allow, or we need to protect against the risk of any overpressure of the condensate pipework downstream of the steam trap. So a flash steam vent, typically that is going to take place on top of a condensate recovery pump. So we can allow for that pressure drop. We can allow for the condensate to fall out as a single phase, at which point it can be pumped. But of course, if we can condense as much of that flash steam as we possibly can, or better still, add it to another process, not only are we improving the overall energy efficiency, but we're helping to keep the condensate return volume as high as we possibly can, thereby allowing for the steam condition to be held at the highest possible rate. But we also know that condensate is quite often knowingly dumped to waste through fear of the fact that we don't want it to contaminate the steam boiler, where it could cause a failure, a mechanical issue, and contaminate steam that could then be distributed out to other processes. And it's just to remind us that we can identify when that condensate is at a risk of being contaminated by using either a turbidity probe or a conductivity probe. And if that sends a signal to a diverting valve ahead of the process or ahead of the condensate return network, we can dump that contaminated condensate to waste. It means we're protecting the steam boiler, but it also means that whenever the condensate is in an excellent condition for recovery, we can do so. So I'd just like to summarise very briefly on what we've gone through today and what the learning outcomes are. We know that the principal raw ingredient of a steam system is the water itself. The quality of the water is critical. If we're using a poor condition of water in a well-designed boiler or even in a chemical-free clean steam generator, it means that we're simply not going to get a good condition of steam being produced. The water quality is fundamental. When we're talking about a good condition of steam, typically we mean that the steam suits the requirements of the application, and that can vary depending upon whether we're using steam for a basic instantaneous plate heat exchanger, or whether we're using the steam for directly injected into a pharmaceutical or a food product, for example. So we know we need to keep the steam at a high condition, at a good quality for heat transfer purposes. Typically, we're talking about keeping the steam as dry as we possibly can and free of air. It's only by doing so that we can guarantee that we're operating close to the steam table values. We know that good condition of steam, it starts in the boiler house at the point of generation, but we need to observe good working practice to distribute the steam so it arrives at the process in the best possible condition. We want to get the condensate away so it doesn't flood the process, and we want to get it back to the boiler house where we can keep the feed water at a nice high temperature. We can protect against that condensate being needlessly dumped to waste. But the most important factor is we need to take a step back and we need to examine the risk that steam could pose to an environment if it's likely to be contaminated with an excess of moisture, air, and boiler chemicals. If there is a risk that that steam could contaminate a product or atmosphere, we need to move up the steam condition triangle and generate chemical-free steam utilizing that clean steam generator. So I'd like to thank you very much for the time that you've spent with us today. It's at this point I'd like to ask Steve if you could open up the microphones and address any questions that there may be.
Yeah, hi Dan. Thank you for another excellent presentation. Very well delivered, very clear, lots and lots of information there. We do have a number of questions come in, actually. I'm just conscious of the time, so I've just selected probably the most pertinent two, if I can put it that way. So the first one that's come in is on the steam condition slide, you showed that food and beverage applications may use either filtered steam or clean steam. What factors would decide whether one or the other was used, and how effective is the filtration that's used?
Okay, a good question. Well, filtered steam has been used in previous years in the food and beverage industry, but it's starting to lose favour for a number of reasons. The first reason is, well, it's very, very difficult to guarantee that the steam that is being produced downstream of the filter will meet BSEN 285 requirements. And a filter, well, it's a mechanical device. So all we're actually doing is we're taking out particulate. But we're not removing all of the particulate, we're just removing it down to a certain size. For example, anywhere between 5 and 10
is on.
So it's also it does require mechanical cleaning from time to time, something that's not always done, and that can result in a pressure drop at the process. So engineers quite often attempted to remove the element and then dispose of it, at which point we're no longer getting filtered steam. The only way we can guarantee that we're providing steam that isn't at risk of being contaminated and will adhere to those BSEN 285 standards is by producing chemical-free steam in a clean steam generator.
Okay, so it really gives us that guaranteed quality that we're after then. Yeah, okay.
Absolutely.
Excellent. Okay, lovely, great, good, thank you. And there's a further question. I'm not sure if this is an easy one to answer, so apologies if this is a little bit of a long-winded answer. But there's a question from Marco with regard to air venting specifically. So in respect of air removal from distribution, how many air vents do we need to remove air completely? And is there a rule of thumb that we can use?
Crikey, that is a good question. typically, and I'm talking about a plant steam system here rather than a clean steam system, typically we want to vent the air at the occasional high point. So if the steam is going up a riser, that's where the air will naturally climb to. We want to vent the air away at that point. It's good practice to vent the air away at a separator. Separators have got a drain point at the low point to remove the condensate towards the steam trap. An air vent should always be located at the high point. The very, very end of the various distribution legs, that's where the steam will push the air to in like the piston effect, and also at the process. So we're saying like a steam heat exchanger, for example, at the opposite side to the steam inlet, because that's where the air will be pushed to by the motive action of the steam.
Okay, that's great, lovely. Thank you, Dan. Very good answer there. Yeah, that's just we're slightly over time, so we'll end the questions there if that's okay. I don't know. I can see that Brian's just been able to join us finally. If Brian's able to join with audio, that'll be great for maybe some closing comments, or perhaps if not, yourself.
Hi guys, can you hear me, Dan?
Yes, we can.
Yeah, yeah. Apologies for not making it in at the beginning of the presentation, but I'm sure you guys did a brilliant job. So I'd just like to offer some personal thanks. Now we're at the end of the program. Thank you, Dan and Stephen, for a most professional job. We didn't expect any less, but it's absolutely brilliant. I think it's a big thank you to Spirax Sarco, who are doing what any great UK company would do, which is support engineers in the UK and internationally in a really positive way. I'd like to thank the guys down at Birdcage Walk, especially, I'm not sure who's on today, but Fiona's done most. I'm not sure that it was Natalie that's on today. But thanks to the team in Birdcage Walk, and also Nikki, our Yorkshire regional admin, who does a great job day in, day out for the IMechE in Yorkshire. And a real big thank you to all those folk that have dialed in. Hope you found them interesting. I'm sure they will be available on YouTube, and I'm sure we'll hear from Dan again in the not too distant future. Any closing remarks, Dan?
No, just to thank yourself, Brian, and everyone at IMechE for arranging this suite of presentations. If there's any appetite at any point in the future, whether for IMechE or whether for your individual practice, please don't hesitate to get in touch with your local sales engineer. If there are any questions that do require any further comments, please reach out to me, and I'll be happy to support further.
Brilliant. Thanks, Dan.
Thank you.